Hi everyone! Today we're going to learn all about earthquakes and seismic waves. So today we're going to talk about what is an earthquake, how does an earthquake happen, we're going to talk about the different types of seismic waves that result, how to figure out where an earthquake started, and finally, how can we use seismic waves to help tell us about the interior of the Earth. So first of all, we need to know what is an earthquake. The Earth's crust is made up of solid rock. And it's under continual motion, which means there's going to be a lot of forces that build up. These forces are called stresses. This can result in the rock actually deforming, which is called strain. Now sometimes there's a certain amount of strain in a rock, a certain amount of stress that results in strain, I should say. And what will happen is the rock will behave kind of like an elastic. It will snap back. When it snaps back, the plane along which it will do that is called a fault line. And when it snaps back, there's often a lot of energy released, and that energy can be released in the form of seismic waves. Now, a rock won't always behave elastically. There are some situations where there's so much force, there's so much stress exerted on a rock that it will actually crack. It will actually fracture. That will also happen along what's called a fault line, and that will result in seismic waves as well, an earthquake. Now there are all different kinds of earthquakes. You can have little earthquakes, like this example from Kent from several years ago, or you can have large earthquakes. There are a few different scales that exist to measure the intensity of earthquakes. The first one is called the Modified Mercalli Intensity Scale. This is an older scale, and it's typically good because it's easy for the general public to understand what the different numbers mean. The detriment is it's pretty arbitrary, and it will differ depending on the population size and the types of buildings in a certain area. So for example, on this particular scale, a weak earthquake, level 3, would be felt noticeably by people indoors. However, many people don't realize it's an earthquake. Standing motor cars may rock slightly. Vibrations could be similar to the passing of a truck. Whereas a level 9 earthquake would be classified as violent, damage considerable in specially designed structures, well-designed frame structures thrown out of plumb. This obviously depends very much on the structures that are present. So obviously this wasn't a great scale to use for everyone. There is a better scale. It used to be called the Richter scale. Now it's called the moment magnitude scale. It relates to the energy that's released by an earthquake. It's calculated by measuring the amplitude of the seismic waves, measured by a seismograph. We'll talk about those in a few slides, while also taking into account the elasticity of the surrounding rock, the surface area of the fault that slips, and the distance that the rock travels along the fault. This is a logarithmic scale, so for every whole number increase, the magnitude of the quake actually increases by 10 times. So a 4 magnitude earthquake would be very minor, minor shaking, whereas a 9 magnitude earthquake on this scale would be absolutely horrifically destructive. There are a few different kinds of faults that you can have. You can have a normal fault, where we have land sliding down with gravity when this particular piece of crust has great stress exerted on it. You can have a reverse fault, where the piece of crust actually slips up against gravity. And you can have something called a strike-slip fault, which is associated with pieces of crust moving side by side. Before we talk about seismic waves, we need to talk about what is a wave in general, a mechanical wave. It's a transfer of energy through a medium where particles are moving with respect to each other, but there's not one single particle that goes from point A to point B, like throwing a baseball from one person to the other. Let's imagine this line of cars. The blue car is cruising along towards a stop sign. The cars in front of it are stopped. The blue car doesn't notice that the light has turned red. It's going to hit the first car it sees. That car is going to hit the car in front of it. That car is going to hit the car in front of it. So effectively, energy is transferred down the line, even though the blue car never went from point A all the way to point B. This is a lot how particles will move in a medium when energy is transferred via a wave. So in order to understand different types of seismic waves, we have to look at different types of mechanical waves where particles are moving back and forth and energy is transferred through a medium. The first type of mechanical wave we're going to look at is called a longitudinal wave. In this example, particles move back and forth in the same direction that the wave propagates. So you'll notice in this animation, the wave itself is moving left to right. However, every individual particle is just moving back and forth, left, right, left, right. In the animation below it, we're looking at a transverse wave. In this particular wave, again, energy is transported left to right, but every individual particle is just moving up and down. So a longitudinal wave has particle motion in the same direction as wave propagation, whereas a transverse wave has particle motion perpendicular to the direction of wave propagation. These are actually two important types of seismic waves. The last type of seismic wave that's very important when you're talking about how we experience earthquakes is called a surface wave. Notice how this one has a huge amplitude at the surface. And by the way, the gray part represents the solid crust. So the amplitude is greatest at the surface and the amplitude gets smaller the deeper you get into the Earth's crust. Now in terms of seismic waves, these three types of waves have special names. Longitudinal and transverse waves can travel through solid rock all the way through the Earth. Well, all the way through the mantle at least. Surface waves can only travel along the surface of the Earth in a large enough amplitude to be felt. So which one do you think is more destructive? Well, taking a look at the animations from the last slide, if you were standing on the surface of the ground and a surface wave went by, you're definitely going for a ride. So surface waves are the most destructive type of seismic wave. Longitudinal waves, ones where particles are moving in the same direction as the wave propagation, are actually the fastest type of wave to travel through solid rock. So they're called primary waves. Primary because they're always the first to reach any location after an earthquake has happened. Transverse waves are called secondary waves because they travel a little bit slower than longitudinal waves. So these transverse waves are the second fastest, so they're called secondary waves. They arrive second. And finally, surface waves. These guys are the most destructive, and they arrive last at any location after an earthquake has happened. A couple of definitions next. The focus is the actual location along a fault line where a slip has occurred. That's where the actual energy is emanating from. The epicenter of an earthquake is just the location on the surface of the Earth directly above the focus of the earthquake. A seismometer is a device that can record vibrations in the ground. At its simplest, we can imagine it as a scrolling piece of paper that's fixed to Earth's crust with a freely dangling pen on top. The pen stays still, but the scrolling piece of paper can move when an earthquake is nearby, resulting in a whole bunch of squiggles on the piece of paper. Here's an example of what a seismograph might record. Let's say an earthquake happens. Our recording station is a certain distance from our earthquake. The first type of wave that's going to hit us is the P wave, the longitudinal wave, because it travels the fastest. It has the smallest amplitude, so it's only going to result in a little bit of shaking. A little while later, the S wave, the secondary wave, hits us. That's the transverse wave. It traveled a little bit slower, so it took a little bit longer to get there. It typically has a slightly larger magnitude of shaking. Last to arrive are the surface waves. They travel the slowest, but they pack the biggest punch, so they result in the most shaking. Now, since these different waves travel at different speeds, we can actually figure out how far away an earthquake was depending on how far apart the spacing of arrival of these waves are at our seismometer. The farther away they are from the epicenter, the further apart in time they're going to be spaced, as recorded on our seismograph. Seismologists use a time travel graph to make this process easier. On the graphs, you can determine how far apart in time the primary and secondary waves are, and therefore determine how far away the earthquake was. Here's an example of that kind of a graph. The P wave is represented as the blue line. The S wave is represented as the red line. The y-axis represents the time since the earthquake occurred, and the x-axis represents how far away we are from the epicenter. So let's say I'm 100 kilometers away from the epicenter. It's going to take about 12 seconds for that first wave to hit, that primary wave. And it's going to take about 23 seconds since the earthquake happened for that secondary wave to hit, which means there's about an 11-second difference, about 12 seconds to 23 seconds. So an 11-second difference between the arrival of those two types of waves. If I know there's an 11-second difference between the arrival of those two waves, I can look on this graph and I can tell I'm 100 kilometers from the location of that earthquake. Here's an example of a seismogram reading. Let's say I'm at my earthquake measuring station and I've recorded the following wave. The first blip is my primary wave, the second blip is my secondary wave. I have no idea of knowing exactly when the earthquake started. The only thing I can determine is what is the spacing in time of the arrival of these two waves? Well, from my arbitrary time scale, the P wave arrived at about 60 seconds. The S wave arrived at about 115 seconds, which means that was a difference of about 55 seconds. Now we can use our time travel curve to figure out exactly how far away the earthquake was. So I'm going to use some tools on this computer to help me figure that out. I'm going to make a line on this graph just to help me out. That is about 55 seconds tall, and I'm just using the y-axis to measure this. So right about there. So that's the spacing of my P and S wave. Now I got to figure out, where does this fit? Right about here. This location in my time travel graph represents when the P and S wave are spaced by about 55 seconds. Reading down, I can see that this occurs only if I'm 560 kilometers away from the earthquake. Therefore, I'm 560 kilometers away from my earthquake. One important thing to notice is, if I use this diagram, I don't know what direction the earthquake is in. I only know that it was 560 kilometers away, which means I'm here at my recording station. The earthquake could have happened anywhere along the circumference of this circle. I only know it's 560 kilometers away. So if I only have a single seismograph worth of data, I don't know exactly where the earthquake is. In order to figure out exactly where the earthquake is, where is that epicenter, I'm going to need 3 different recording stations to tell me exactly how far away the earthquake was from them. So for example, if someone in Japan records this distance to an earthquake, they only know the earthquake could have happened anywhere on the circumference of this circle. But if someone else does it in Australia, they could tell you the earthquake is anywhere on the circumference of this circle. If someone else does this in the United States, they could tell you the earthquake is anywhere on the circumference of this circle. There's only one location where all 3 circles intersect, and that's this one right here, which happens to be near the Hawaiian Islands. This is called triangulation, and that's how you can figure out exactly where an earthquake is. This is an interesting website I want to show you. You're going to be using this for your earthquake assignment. This is a USGS website that can actually tell you the most recent earthquakes that have happened around the world. We can also filter earthquakes that have happened in the last 30 days, in the last 7 days, or in the last day. I'm going to look at the last 7 days large earthquakes. And now I'm just going to pan around the world. Take a look at these dots. The dots represent different magnitudes of earthquakes. And I want you to notice where they're located. Are there a whole lot in the middle of a tectonic plate? Nope. They're mostly clustered around the fault lines. And that makes sense, because that's where the plates are rubbing against each other the most. That's where there are the most stresses and therefore the most chance for those plates to be slipping and creating an earthquake. So here's a map of our tectonic plates. And if you were to look at a plot of all of the earthquakes that have happened over the last year, you're going to see they largely trace out an outline of all of our tectonic plates. Now we're going to talk about some interesting properties of seismic waves and how they can tell us about the interior of the Earth. Before we talk about how they can be used to determine what the interior of our Earth looks like, we're going to need to talk about some properties. First of all, when a wave travels through a medium, the speed of the wave depends on the type of the wave, as well as the density of the medium and the elasticity of the medium. So the elasticity of a medium means how tightly are the particles in that medium held together. Density means how massive are the particles, or how massive is the material per unit volume. More elastic materials will allow waves to travel faster. More dense materials will slow a wave down. Here's what happens inside the Earth. Given the inside of the Earth, the solid part of the inside of the Earth, the speed of a seismic wave increases with depth. So keep that in mind when we're looking at the next example. Here's another thing I want you to remember. Refraction. When a wave travels from one material to another material, where the speed of propagation changes, the wave will also change direction, and that's called refraction. We're going to take a look at this interesting simulation, which models a wave traveling through a medium. I want you to imagine this looks a little bit like ripples on a pond. This simulation can be used to model sound waves, light waves. In this case, we're going to pretend they're seismic waves. In this simulation right here, the dark blue color represents a medium where the waves travel slowly, whereas the light blue color represents a medium where the waves can travel faster. So if this were the interior of the Earth, the top of this simulation would be closer to the surface. The bottom of this simulation would represent deeper in the Earth's crust or mantle. Notice what's happening. The direction of the wave changes. It actually bends away from the normal as it travels faster and faster, which means the deeper that a seismic wave probes into the interior of the Earth, the more it refracts and bends away from the normal. The other thing to remember is that waves can also reflect. They can also bounce off of any abrupt discontinuity inside our Earth. Keep in mind, our Earth is made up of a bunch of discontinuities: crust, mantle, outer core, inner core. If the interior of the Earth were made of only one type of solid, we could expect all of the seismic waves to travel in perfectly straight lines, just like in this diagram. Of course, we know that's not the case. If the interior of the Earth were made up of something that had the same composition, but just got more dense as you got to the center of the Earth, seismic waves would travel like this. They would undergo refraction. As they got deeper, they would refract away from the normal until they eventually hit the surface again. This is also not the pattern we see when we look at seismic waves traveling through the Earth. Therefore, this isn't what the Earth looks like on the inside. Here's an example of what the Earth actually looks like on the inside and how primary waves, which are longitudinal waves, travel through the interior. Notice that they will curve because they will refract as they travel faster and faster the deeper they get into the mantle. Look what happens once they reach the outer core. Keep in mind the outer core is a very abrupt change from dense plastic material to a liquid that's also even more dense. There's a massive discontinuity, and again we have refraction through the outer core, which is a liquid, and then another discontinuity as the P waves pass back into the mantle. What this ends up showing is a whole region on the Earth where you're not going to get any P waves, depending on the location of your earthquake. It's called a P wave shadow zone. Something even weirder happens with secondary waves, S waves, because S waves can't travel through liquid at all. So once an S wave hits the outer core, which is a liquid, they stop completely. They can reflect off the outer core, but they can't go through it. So you will detect no S waves on this entire part of the Earth. That's a big hint as to the composition of the inside of our Earth. That's telling us the outer core is a liquid. Here's an interesting simulation of this in action. Here's a cross-section of our Earth. Let's start our earthquake. Notice that our P wave front is the fastest, followed by our S waves, secondary waves. Once the P waves hit the outer core, some are going to pass through, but some actually bounce off. When the S waves hit the outer core, none can pass through, but some can bounce off. Now, if I spin the Earth around, we can only see the surface waves when we look at the surface of the Earth. Here's our P wave front making its way across the surface of the Earth, ready to be detected by seismic recording stations. Here are our secondary waves traveling across the surface of the Earth, going a little bit slower than our P waves. And here are surface waves, causing the most destruction and traveling the slowest across the surface of the Earth. Now, if I flip it back around, look how messy this looks. We've got multiple reflections heading off of all of the different discontinuities inside our Earth. But if you analyze this, it'll actually tell you what's going on the inside of their Earth. The other interesting thing to note is that looking at seismic waves can actually help us probe other planets as well. The trick is you just have to land a sensor there first. Well, that's it for today on earthquakes. See you next time.